Here's a simulation environment that shows quantum tunneling. Here we've got some sort of a particle of energy, total energy, or in this case the kinetic energy would be the total energy that's along this line here. And it's coming into a barrier like a hill. This is just a square hill. But the total kinetic energy needed to get up the hill in terms of Newtonian physics would be about 3 times the kinetic energy that it has. Okay, and so as this particle comes into this barrier, it's mostly reflected back in. Okay, but there's a very small probability, we can't see it very well, but let me magnify it here. There's a very small probability that that particle will make it through. This is according to quantum physics. Now that probability will increase if the energy is closer to the barrier height. The total kinetic energy of the particle is closer to that barrier height, and if it's a thinner barrier. Okay, so let's take a look at this simulation. In this case, there's a very large probability that the particle will make it through the barrier. Okay, and then the other extreme here, this is kind of interesting also. If the hill or barrier is smaller than the kinetic energy, we would expect the particle to just keep on sailing to the right. But let's take a look what happens here. Comes in, and most of it does sail to the right, but there's a small probability that some of the time the particle will bounce back and not make it over the barrier. Okay, so this is quantum physics, the tunneling effect, or the opposite of the lack of tunneling. And this is actually used today by electrical engineers and computer engineers in designing microelectronics. It's not just some wild, weird thing, but it's used, if you understand quantum physics well enough, then you can incorporate that into the design of your computer or computer chips.